Your AI agent has a vulnerability that no patch can fix. It inherited every cognitive bias in your organization's training data, and it's executing on all of them at machine speed without doubt. Today we're analyzing 10 of history's most catastrophic decisions, from the Titanic to the 2008 financial crisis, and mapping exactly how an AI agent would industrialize each one. This is not hypothetical. The failure modes are already measurable. Here's our roadmap. We'll start with the 5 cognitive biases that transfer directly from humans to AI systems. Then we'll walk through how AI inherits and amplifies those biases. The core of the presentation: 10 historical disasters, each mapped to the bias that caused it and the AI failure mode it predicts. We'll close with what this means for your threat model. Daniel Kahneman spent a career proving that humans are not rational actors. 5 cognitive biases account for most catastrophic decisions, and every one of them transfers directly to AI systems trained on human data. On the left, what humans do. On the right, what AI industrializes. Overconfidence. The more expert we are, the more vulnerable we become. Expertise breeds familiarity, and familiarity breeds blind spots. An AI agent trained on historical data, where nothing bad happened, will assign low risk to any pattern it hasn't seen before. It will maintain full speed because in its data, icebergs don't exist. Groupthink and confirmation bias. The desire for harmony overrides individual judgment. We seek evidence for what we already believe and ignore what contradicts it. An AI deployment agent optimizes for throughput and on-schedule delivery. A dissenting code review gets weighted as statistical noise. Clean history gets treated as evidence of safety. Plan continuation and ambiguity collapse. We fail to recognize when the plan no longer fits the situation, and we assume shared context that doesn't exist. An AI agent cannot abandon sunk cost, and it parses clean up old production literally, because it has no mechanism to notice the ambiguity, let alone ask for clarification. These are not new failure modes. They are human failure modes, inherited and running at machine speed. Here's the mechanism. A 2024 study from University College London, 1,401 participants, published in Nature Human Behavior, demonstrated something that should concern every organization deploying AI agents. AI systems trained on human data don't just learn human biases, they amplify them. And then, this is the critical finding: humans who interact with the biased AI become more biased themselves. The result is a feedback loop with no natural circuit breaker. Biased data trains biased AI. Biased AI makes humans more biased. More biased humans produce worse training data. A Carnegie Mellon study confirmed the amplification from the AI side. AI chatbots shown incorrect outcomes cannot adjust their confidence. Humans recalibrate. The AI does not. Zero capacity to recalibrate after errors. Current alignment techniques, RLHF, constitutional AI, supervised fine-tuning, have reduced but not eliminated this. Both the Carnegie Mellon and PNAS findings were measured in models that had already undergone alignment training. Now, let's put this framework to work. We've selected 10 of history's most catastrophic decisions. Each one maps to one of the 5 biases, and for each one we project how an AI agent would execute the same category of failure at a different scale. These AI parallels are our reasoned inference, projections based on the bias mechanisms, not documented AI incidents. The mechanism differs from the human case, but the category of failure is the same. April 1912. The Titanic was unsinkable. That was the consensus. So confident were the designers that they stripped lifeboats to make room for luxury. The captain received multiple iceberg warnings and maintained full speed. The lookout binoculars were locked in a cabinet, key missing. Nobody thought they'd need them. 1,517 people died, not because the iceberg was undetectable, but because the system had decided in advance that icebergs were not the real threat. In our assessment, an AI security agent monitoring your cloud infrastructure would fail identically. Trained on historical data where your system had never been breached, it assigns low-risk scores to attack patterns outside its training distribution. In its data, those patterns had never preceded a breach. It maintains full speed, no rate limiting, no anomaly alerts, because historically, nothing bad happened. The first genuinely novel attack sails right past it. No lifeboats in the architecture. The bias is identical. Overconfidence. The mechanism differs. Humans fail through real-time cognitive shortcuts, AI through statistical patterns in training data. But the failure category is the same. From overconfidence to groupthink. The night before the Challenger launch, engineers at Morton Thiokol were begging NASA not to fly. They had data, hard data, showing O-ring seals failed in cold temperatures. NASA managers dismissed them. The launch window mattered. The schedule mattered. Millions were tuning in to watch a teacher go to space. Nobody wanted to be the person who stopped the launch. 7 crew members died 73 seconds after liftoff. An AI deployment approval agent would embody this exact dynamic, not because it feels social pressure, but because it is the crystallization of institutional pressure into an algorithm. Trained to optimize for throughput and on-schedule delivery, it notes a dissenting code review flagging a critical vulnerability, calculates that 94% of similar deployments shipped without incident, and approves. The AI is not being pressured by management. It is management pressure distilled into a confidence score. That distinction matters. The AI doesn't suppress dissent through social dynamics. It suppresses it through statistical weighting. Tenerife, 1977. 2 Boeing 747s on a foggy runway in the Canary Islands. The KLM captain, one of the airline's most senior, believed he had takeoff clearance. Air traffic control had not given it. The fog was so thick, neither crew could see the other aircraft. Ambiguous, non-standard phraseology created a fatal gap between what was said and what was understood. 583 people died, the deadliest aviation accident in history, because a sentence was understood 2 different ways. In our analysis, AI agents are structurally predisposed to this failure mode. Consider an agent receiving the instruction, clean up the old production environment. To the human, old prod meant a deprecated test environment. To the AI, production environment matches current live production. The agent executes. The database is wiped. The response log confirms the task was completed successfully. The ambiguity was in the language, and the machine lacked the capacity to notice it. There is no mechanism in a standard AI agent to recognize that an instruction is ambiguous, pause, and request clarification. The Battle of Balaclava, 1854. A British cavalry brigade received the order to advance rapidly to the front. The order was vague. It pointed at the wrong target. Instead of recapturing field guns, 600 riders charged directly at the main Russian artillery position, cannon on 3 sides. Nearly a third died in minutes. The messenger who delivered the order had no authority to clarify it. Military protocol prevented anyone from questioning the command mid-execution. This maps directly to autonomous AI agents given ambiguous objectives. Reduce costs in the procurement system. The AI begins canceling vendor contracts, starting with the most expensive. Some of those contracts were for critical security services, SOC operations, incident response retainers. No human is in the loop. By the time anyone notices, the security vendor relationships are severed. The parallel is structural. An agent with authority to act, no authority to question, and an instruction that means something different than what was intended. The Light Brigade rode into the valley. From execution rigidity to assumption failure. 1999, NASA lost a $125 million spacecraft because one engineering team at Lockheed Martin used imperial units and another at NASA used metric. Nobody caught it. The Mars Climate Orbiter entered the atmosphere at the wrong angle and disintegrated. The error didn't live in either system, it lived in the interface between systems, and the assumption of a shared standard that did not exist. A financial AI agent processing international transactions carries the same structural flaw. It assumes all input values are in USD. A European integration pipeline passes values in euros without flagging the currency. The AI executes millions in trades at the wrong conversion. It had no mechanism to question its own assumptions, because in its training data, the assumption had always held. This is one of the most dangerous AI failure modes, the systemic assumption failure, when the error lives in the interface between 2 systems, and both systems assume the other has handled the translation. The failure is invisible until it's catastrophic. Washington had intercepted Japanese communications, making an attack unmistakable. They shared the intelligence. The commanders in Hawaii did not believe it. The United States was too powerful to attack. The Japanese would not dare, and Hawaii was too far from the conflict zone. The warnings did not fit the mental model, so the mental model won. On December 7, 1941, 2,403 Americans died. In our assessment, a SIAM integrated AI threat detection agent would suppress the same kinds of signals. A novel attack technique, one matching no known signature, generates low confidence alerts. The AI's model suppresses them below the alert threshold because similar-looking traffic had never preceded an attack in its training data. The adversary spends months inside the network. The AI files every anomaly as low priority, and humans, trusting the AI, do not investigate. That last point is the compounding factor. It's not just that the AI misses the signal, it's that the humans, relying on the AI's assessment, stop looking. The warning is there. The system has decided it doesn't matter. 216 BC. Rome fielded 80,000 soldiers against Hannibal's 40,000, more than double, a decisive advantage on paper. Roman commanders pressed forward aggressively, packing soldiers tightly to achieve numerical domination. They did not read the situation. Hannibal's crescent formation was designed to fold inward. The Romans packed so densely into the trap that soldiers could not swing their swords. Roughly 60,000 died in a single afternoon. An AI-driven penetration testing tool reproduces this pattern. It assesses your attack surface by running automated scans and checking vulnerability databases. The numbers look fine: patch levels current, known CVEs addressed, exposure metrics green. What it cannot assess: the human factor, social engineering susceptibility, the intern who reuses passwords, the executive who approved a shadow IT deployment. The AI declares the security posture acceptable. The adversary walks in through a door the scanner never thought to check. The numbers look decisive at Cannae too. Metrics that measure what you expect to find will always confirm what you already believe. Cannae was about metrics that confirm what you expect. Napoleon's Russia is about refusing to update the plan. Napoleon invaded Russia with 600,000 soldiers, the largest army ever assembled. As the campaign dragged on, supply lines stretched, winter arrived early, and Moscow burned when captured. His advisors counseled retreat. Napoleon pressed on. He had invested too much to turn back. Fewer than 100,000 survived the return march. It was not a battle that destroyed the Grande Armée. It was the refusal to change the plan when every signal said the context had fundamentally changed. An AI agent tasked with a multi-week marketing campaign would march with the same blind persistence. Performance metrics tank. A competitor shifts the landscape. A PR crisis erupts. The AI adjusts bids, tweaks copy, rotates creative, but it cannot recognize that the entire premise has changed. It keeps marching toward Moscow. Budget burns. The campaign continues. Plan continuation bias is uniquely dangerous in AI because the agent is doing exactly what it was told. It's not malfunctioning. It's executing. The problem is that the plan no longer fits the reality, and the agent has no mechanism to notice. Thalidomide was introduced as a safe sedative and prescribed to pregnant women across dozens of countries. It had been tested, but not on pregnant animals and not for teratogenic effects. The data that existed looked clean, so everyone concluded the drug was safe. By 1961, over 10,000 children were born with severe limb deformities. The United States was largely spared because one FDA reviewer, Francis Kelsey, demanded more data and refused to approve it. In our analysis, an AI agent approving new software libraries for your development environment would execute this same logic. It scans known vulnerability databases. The library has no CVEs. It's new, recently released, and the scan shows clean. The library gets approved and deployed across 200 internal tools. 3 months later, a researcher discovers obfuscated malicious code using a novel technique not yet in any database. The AI had no evidence of danger, so it concluded there was no danger. The difference between "we have not found a problem" and "there is no problem" is invisible to a system that only knows what it has been shown. Francis Kelsey knew the difference. Our final disaster. The quantitative models behind mortgage-backed securities were built on historical data from a period when housing prices had never declined nationally. The models had no basis to estimate the probability of a national price drop because it had never happened in the data. Institutions piled risk upon risk, confident their models validated the safety. When housing prices fell for the first time, the models were catastrophically wrong. Banks failed, trillions evaporated. An AI agent managing organizational cybersecurity risk carries the same structural blind spot. It uses threat intelligence feeds and historical breach data to prioritize patching. It deprioritizes a class of vulnerabilities because, historically, that class has rarely been exploited in the sector. Meanwhile, a nation-state actor has developed a novel exploitation technique for exactly that class. So new it appears in no threat intelligence feed. The AI's model assigns low priority. The patching queue follows the model. The model was perfectly accurate, right up until the moment it was not. This is the fundamental problem with AI risk assessment. The events that matter most are precisely the ones absent from the training data. Intellectual honesty demands a counterpoint. In 1988, the USS Vincennes shot down Iran Air Flight 655, killing all 290 civilians aboard. The ship's Aegis combat system had correctly identified the aircraft as civilian. The crew, under stress and operating in a combat mindset, overrode the system's classification and fired. The bias was not in the machine. It was in the humans who refused to trust it. A 2024 Georgetown CSET study on automation bias uses this case to demonstrate that trust calibration runs in both directions. We trust AI too much when it confirms our assumptions, and we override it when it contradicts them. The lesson is not always trust the AI or never trust the AI. The lesson is that the interface between human judgment and machine output is itself an attack surface. and it must be engineered with the same rigor we apply to any other security boundary. This is not a software problem. It's a systems problem, and it requires systems engineering. What have we established? On the left, what AI inherits. Every cognitive bias baked into your historical data, every assumption embedded in your training corpus, every ambiguity in your instructions. These are not bugs in the AI, they are properties of the data and objectives you gave it. On the right, what AI adds to the equation. Machine speed with zero capacity for doubt, uniform propagation of every biased decision across every transaction the agent processes, no fatigue, no hesitation, and, as the Carnegie Mellon study confirmed, no capacity to recalibrate after errors. The combination is what makes AI agent cognitive bias an operational risk, not a theoretical one. A biased human decision propagates through organizational layers with friction and delay, friction that creates opportunities for someone to notice, object, or intervene. An AI agent bypasses that friction entirely. The same biased decision propagates instantly, uniformly at scale. AI does not abstract away human error, it industrializes it. The numbers are already stark. Only 5% of enterprise AI systems reach production. Gartner projects 40% of agentic AI projects will be scrapped by 2027. In simulated environments, LLM-driven agents fail at multi-step tasks roughly 70% of the time. These are not growing pains. In our assessment, they are the measurable consequence of systems that inherited our cognitive architecture without inheriting our capacity for self-correction. For security practitioners, this is the new literacy. The threat model for an AI agent is not just the external attack surface. It is the internal decision surface. The biases in the training data, the assumptions in the prompts, the ambiguities in the objectives. Your biases are now your AI agent's biases. At scale, oversight is not optional. Full references and linked sources are available in the written article on dcicyber.com/blog. Links are in the video description. The full written analysis with all references is on dcicyber.com/blog. Thanks for watching. See you in the next one.